All right, let's talk about one of the most critical and honestly, one of the most overlooked engineering problems in AI today, the chunking disaster. This is that hidden landmine that can make a brilliant AI give a catastrophically wrong answer. And if you've ever built a RAG system, I'm willing to bet you've run into this. It all starts with this totally bizarre paradox. You think, hey, I'll give my AI this huge comprehensive document. More data means smarter AI, right? But then its answers actually get worse. How does that even happen? Well, the answer lies in something we call the Goldilocks dilemma. It's all about the art and really the science of chunking. This is the very first thing you do when you're working with big documents. And if you get this wrong, it's like the first domino in a huge chain of failure. So, what is chunking? In theory, it's super simple. An LLM can't just swallow a 100-page PDF whole. It's too slow, way too expensive, and honestly, the model just gets lost. So we've got to chop that document up into smaller, bite-sized pieces, or chunks. The real question is, how big should those pieces be? And this is where we hit our first trap. If you make your chunks too small, you're not just cutting up text. You're literally slicing an idea right down the middle, and you lose all the context that gives it meaning. So, for example, imagine your system finds this one little piece of text from a policy document. The passenger is entitled to a full refund. Okay, sounds pretty good, right? Crystal clear. The AI sees this and goes, great, full refunds for everyone. But uh-oh, that's only half the story. Because the very next chunk, which the system might not even see, has the killer condition, only if they apply within 24 hours. By just splitting that one sentence, you set up your AI to confidently give a completely wrong and potentially very expensive answer. That's the danger of going too small. So, you might think, okay, easy fix. I'll just make the chunks bigger. Not so fast. Going too big is just as dangerous. When you force a model to sift through a massive wall of text to find one tiny fact, you run straight into a well-known weakness of LLMs called the lost in the middle phenomenon. It turns out that LLMs, kind of like us, have a limited attention span. They have a really hard time remembering details that are buried in the middle of a long piece of text, and we can actually see what this looks like. Take a look at this graph. This is the attention U-curve, and it is so important to understand. You've got answer accuracy on the side and the position of the fact in the text along the bottom. And you see this pattern, right? The model is fantastic at remembering stuff from the very beginning and the very end. But that giant dip in the middle, that's the danger zone. And we're not talking about a little blip. If your key piece of information is buried in that middle danger zone, you could see the accuracy drop by 20 to 30%, maybe even more. Just think about that. In your attempt to give the AI more context, you can accidentally make the right answer completely invisible to it. This leads us to what should be a core rule for anyone building RAG systems. More context does not equal better answers. Precision beats volume every single time. It is so much better to find the one perfect paragraph and give that to the model than to make it search through the entire book. Okay, so let's get out of the theory and look at a practical, high-stakes example of how this all goes wrong. This is the story of the SkyStream disaster, and it is the perfect cautionary tale about the real-world cost of naive chunking. So here's the scene. A parent is using the SkyStream Airlines AI assistant. Their question is simple enough. My 10-year-old is flying to London by themselves. What form do I need? The answer, of course, is buried somewhere in a 30-page policy PDF. Now let's look under the hood at the engineering failure. SkyStream is using what we call a naive, fixed-size chunker. All it does is just chop the document up every 500 characters, no matter what the text actually says. And this clumsy, mechanical process takes the most important rule about kids flying alone and, you guessed it, splits it right in half. So the first chunk says you need the standard UNAC-1 form, but the second chunk, which is now floating off on its own, has this huge exception. For flights to the UK, you need a special UK Border A form. The AI search finds that first chunk, it's a great match for flying alone, but it completely misses the second UK-specific chunk. And the results is an absolute nightmare. The AI confidently tells the parent to use the standard form. The family does exactly what it says, and their child is detained by border control at Heathrow Airport for having the wrong papers. I mean, this is a serious real-world disaster caused by what looks like a tiny engineering decision. So how do we stop this from happening? How do we build systems that are actually reliable enough to handle these critical details? Well, the answer is to stop chunking arbitrarily and start chunking by meaning. Let's just compare these two methods side by side. Fixed size chunking is totally arbitrary. It's just counting characters. But semantic chunking is context aware. It actually tries to understand the text to find the natural boundaries of an idea, like the end of a paragraph or a section. So while the old naive way breaks rules apart, a semantic approach is designed to keep complete ideas, like that crucial rule about UK travel, perfectly together. And that really brings us to the main takeaway here. Building a RAG system that you can actually trust isn't just about dumping data into a folder. It requires really thoughtful, sophisticated engineering. You have to fine-tune your chunking, you have to perfect your retrieval logic, and you have to be constantly testing for exactly these kinds of failures. RAG is an amazing tool, but as we've just seen, it can be really brittle. Trying to perfect information retrieval is an incredibly hard engineering problem. And it kind of makes you wonder, instead of spending all our energy trying to teach models to read better, maybe it's time we also started teaching them to think differently. But hey, that's a whole other conversation.